Hi students, I'm going to debrief some of the parts which we left off yesterday, but before that, um, shall we take a look at the typos which I've informed you yesterday? So question 1, the typo is here. So it's supposed to be substrate. I think I mentioned it over the lecture, so just take note of it. And some of you actually pointed out to me that for question 9, am I trying to ask SN2 here? Because for the whole context of part C is about SN2. Yeah, but if you realize, regardless of whether is it SN2 or SN1, the leaving group or the strength of the C halogen bond affects the rate of nucleophilic substitution. Yep. So doesn't really matter whether it's SM or SM2. However, I think to fit the context, maybe SM2 is a better representation here. Okay, so if you wish to, you can change to SM2. Okay, next we'll go on to solvent effects. So for solvent effects, if you read through the whole thing, you realize that in general, we can classify solvents in 3 categories. They are either polar protic, polar aprotic, or non-polar. So for protic solvent, basically these are solvents that are capable of forming hydrogen bonds, okay, via its OH or NH group. Okay, so you need to know that when they satisfy this criteria, right, they are able to solvate both cations and anions well. Okay, you can think about why, or if you wish to, you can read a little bit about it. For polar protic solvents, basically they are not capable of forming hydrogen bonds, but they have a net dipole moment. Okay, and then non-polar solvent, as the name implies, they are non-polar. Okay, so for question 10, of course, your role here is really to classify them as polar protic, polar aprotic, or non-polar. I think it might be a little bit clear cut here. So before that, maybe I choose a highlighter, maybe in blue. Okay, so I'm going to highlight maybe the clear ones, which is the non-polar solvents. Okay, so non-polar solvent, I think it's pretty clear cut. Compounds largely consisting of non-polar bonds. So in this case, I call hexane. Okay, so hexane is likely to be one because all the CH bond are uh, non-polar in that sense. Okay, another clear-cut example with benzene. Okay, CCl4. If you are very strict about it, okay, CCl4 because as a whole there's no dipole. Okay, and of course CO2. Okay, then next if we go on to look at polar aprotic, so those that are not capable of forming hydrogen bonds. Okay, so what you need to look out for is compounds that does not contain an H or OH group. Okay, so I think if you these are some of the compounds which you're supposed to know the structures. For example, propanone. Okay, trichloromethane, cyanomethane. Okay, HFPA as well. Okay, DMSO, ether. Okay, what about DMF? What about DMF? This is a common misconception. DMF, some students thought that it can form hydrogen bonds, but nope, it can't form hydrogen bonds. Why? Because it does not contain that particular criteria. This is a CH bond, so this is not a H bonded to N or O. Okay, so DMF in this case, for classification purpose, we also classify it as polar aprotic. Okay, so those that are capable of forming hydrogen bonds, of course, is water, ethanol, uric acid, and that's about it. Okay, yep. Let me just emphasize that the solvent effect is not in your current H3 curriculum. Okay, it's not. However, they can give you a context and test you on it. Okay, so now let's look at table 5. Table 5 provides the relative rates of SN2 for this particular compound, 1-bromobutane, okay, with N3 minus. N3 minus is actually an interesting nucleophile. Okay, if you wish to, you can try to draw the structure, okay, on your own. Okay, N3 minus is a very versatile compound. I wouldn't want to go into details, but yeah. Okay, it's known as azide, for those of you who are interested. Okay, so you realize that N3 minus, right? The rate is the fastest in HMPA. Okay, so it's the fastest. Okay, and it's actually the slowest in solvents that are capable of forming hydrogen bonds. Okay, so now the question is, using the table, the information provided in table 5, briefly explain how to change in the solvents. Okay, so notice the non-typos here. This is supposed to be solvent. So just how the change in solvent affects the rate of SN2. Okay, so this should be solvent. My apologies. Okay, affects the rate of SN2. So a sketch of the energy profile diagram is important in supporting your answer. So you realize that for polar protic solvents, if we go back to this example, you notice that polar protic solvents, right, is actually able to solvate an ion well. So what does it really mean when we say that it's able to solvate an ion well? So that really means that it can stabilize it. Okay, because solvation does actually involve the solvent molecules surrounding the anions and forming stabilization interactions. So in this case, it's ion dipole interaction. Okay, so let me just give you an example. So for example, if I have nitrite, so if you try to draw the structures, it will look something like this. Oops, just give me a while. Um, okay, this is plus, this is minus, minus. Okay, then you have the H here, water molecules capable of forming hydrogen bonds. Okay, and then dash. So this is known as hydrogen bonds. Sorry, not hydrogen bonds. I think if you want to be more specific, it should be ion dipole. You can call it hydrogen bonds if you wish to. Okay, ion dipole interaction. Okay, so in this case, this particular interaction, right, sort of diminished the negative charge. So when it diminished the negative charge, the azide is not able to perform its role as the nucleophile as well. So it kind of like stabilizes it. Okay, if I were to stress to you upon this, right, do you realize that it actually resembles the first scenario? Okay, the first scenario where if you notice, the starting point for a not so stabilized anion is actually higher than a stabilized one. Okay, so pathway 1 will represent the pathway for a polar protic solvent. Okay, so for pathway 2, polar aprotic solvent. Okay, so when the nucleophile is well stabilized, okay, the activation barrier to reach the transition state is way higher than one that is not as stabilized. Okay, so I think from here you can actually see that this is shown by the difference in the relative rates. So those that are stabilized, you realize that the rate is way slower than those that are not so stabilized. Okay, so this is the purpose of this whole exercise, is actually to stress upon you that the solvent effect is uh, quite an important one when you want to decide on whether you want to perform the reaction in faster or slower rates. Okay, it doesn't mean faster means better. It really depends, because sometimes it depends on whether your substrate is soluble in the solvent, and sometimes it also depends on the ease of removal of the solvent. So there are a lot of factors that come into play when you decide which solvent to use. Okay, then for the reaction between CH3Y, that's question 12, and X minus, where it can be the various nucleophiles, suggest the reactivity in gaseous phase. So this really is testing you on your knowledge of solvent effects. Okay, so some of you might recognize that HF is actually a weak acid. So therefore, its conjugate base, which is fluoride, it's a relatively good base as compared to the rest. Okay, so without solvent effects, um, there is a correlation between the strength of the nucleophile and its basicity in that sense. So therefore, in the gaseous phase, I would expect chloride to react the fastest, followed by chloride, followed by bromide, followed by iodide. Okay, but when it comes to protic solvents, you will expect the reverse because for protic solvent, right, my fluoride is well stabilized. Okay, so therefore it is not able to perform its role as the nucleophile as well. So in a protic solvent, it's well stabilized. So in terms of the nucleophilicity, so it's lower than chloride, it's lower than bromide, of course lower than iodide. Okay, yep. So this is a direct test of the relationship between the different types of solvent you used, okay, and the nucleophiles. Okay, of course, please do not take this too far. We're just comparing between those in the same groups in the periodic table. Okay, so now briefly explain the nature of solvent, important effect in determining the rates of substitution for SN1. So this is correct, this SN1. Okay, you might realize for SN1, let's say I start off with a simple substrate like this with R group here, and then a leaving group is Cl. Okay, so delta plus, delta minus, this bond breaks, equilibrate to give me a carbocation. Okay, carbocation plus charge. Now you realize that for a carbocation, right, it is a species with a full positive charge. So if it's a species with a full positive charge, definitely the presence of a polar protic solvent where the oxygen can stabilize the positive charge will actually help to lower the activation barrier by quite a bit. Okay, if you can recognize that. Okay, so therefore, for SM1, right, it will definitely work best in the presence of a polar protic solvent. Okay, so yep, that will be the end of the debrief for activity 4 for the remaining question of activity 4. Thank you.